I would like to thank the university for the opportunity to present this lecture today. Now, presenting this lecture at this particular time is special for me as well, as next month marks my 20th anniversary at Heriot-Watt. I joined the university back in 2001 as a postdoc, and you can see here on the screen a selected number of milestones during this time. So in these 20 years, I've had the privilege to work with a number of students and also a number of colleagues here at Heriot-Watt, but also around the world. And I have been involved in teaching, in introducing new courses and new programs, in knowledge exchange with the industry. And I'm mentioning here the IFOA, the Institute and Faculty of Actuaries in particular. And also I have been involved in research. And I will be talking about research today. So my work involves areas in epidemiology, actuarial science, health and life sciences, with the connecting link between these areas being my background in statistical modeling. I've also been fortunate enough to have attracted funding from a number of sources, including various research councils here in the UK, the Institute and Faculty of Actuaries and the Society of Actuaries in the US and the United States, and other sources as well. So, what I want to talk about today is some recent work that we have done on cancer incidence. And this work involves data provided by the Office for National Statistics between, the data are between 1981 and 2016. In the work itself, we have looked at rates for all types of cancer together, and also the four main or most common, if you like, types of cancer: lung cancer, bowel, prostate, and breast cancer. I will be mainly talking about incidence, morbidity, but I will mention a little bit about mortality as well. Mortality is much better documented in the literature for mortality for cancer, but I will be talking about this just a little bit later on. So in this work, the main questions that we wanted to answer was first whether or not there are temporal trends for cancer incidence. In other words, if incidence of cancer increases or decreases with time. We also want to look, and most importantly, perhaps for this work, was the question about whether or not there are differences with respect to region and with respect to deprivation status for cancer incidence. And also, what we wanted to do was to quantify the link, if you like, between incidence and mortality for cancer in terms of the impact of age at diagnosis on number of deaths, on mortality. This work is joint work with a number of colleagues here at Heriot-Watt and also in Southampton. And it has been partly funded by the UK Institute and Faculty of Actuaries and the US Society of Actuaries. So the first question we want to look at is the trend over time. And what we are looking at on this slide, on this graph, is incidence and mortality for all types of cancer. And we're looking at age standardized rates. In other words, these are a weighted average with respect to age, if you like. And we're also looking at what we call crude rates or observed rates. So this does not involve any modeling at this stage. So the main feature of this graph is that if we're looking at the morbidity curves, the incidence curve, so this is increasing both for males and females. But then mortality is actually decreasing over time, and this is good news. And it is decreasing both for males and females. Now, looking at a specific type of cancer now, lung cancer, And this gives us an exception to the trend that we were looking at on the previous slide. So if we look at looking at the incidence, the morbidity rates for males, this is actually dropping. So incidence for cancer, for lung cancer, is dropping for men. Mortality is also dropping for men when lung cancer is concerned. But then if we look at females, look at rates for women, these are increasing. The incidence rates are actually increasing. The mortality rates are actually flat for a long period of time. There might be some slight hint that are decreasing in more recent years, but they are definitely not decreasing as fast as those for men. So, as I said before, the main perhaps question that we wanted to address here was whether or not there are regional and socioeconomic differences in the cancer in the cancer rates that we have looked at. And related to that, if we do find that there are differences, as we will, are these differences big? How big is the gap between perhaps the smallest, the lowest rates and the highest rates? And is that gap getting better, or is it getting worse with time? To answer these questions, we need to now we need to do some modeling, to perform some modeling, stochastic statistical modeling, mainly to account for uncertainty and noise in the data. So this is the most mathematical slide I'm going to show you, I promise. But what we did here was a Bayesian modeling. So we modeled the rates of cancer according to a stochastic model, which assumes that individuals can go from a healthy state to a diagnosed with cancer state. And this transition is actually characterized by a rate theta, an underlying rate theta, which is mainly the rate that we want to estimate using our data. Now, the rate theta itself depends, or may actually depend, on a number of factors. That's what we are actually looking at here. And these factors, the factors that we have looked at, are gender, region, age, deprivation, and time. So this framework, this stochastic framework, allows us to account for uncertainty. Mainly, we do that in this work by looking at probability intervals, credible intervals for the estimations that we have. So let me give you some first results here, some findings that are perhaps not too surprising based on the literature, the results that we have in the literature already. So first of all, is age significant for cancer rates? The answer is yes. The higher, the rates are higher at older ages. And this is something perhaps, as I said before, not surprising. We haven't looked at the graphs that I showed you before. As I said, we were looking at age standardized rates, and this is what we're going to look at later on as well. So we're not actually looking at the age factor. The time variable, the time factor here, I think we've seen already in those graphs, and we will see later on as well, that the incidence is getting higher with time in more recent years, whereas the mortality is getting generally lower. Gender is a significant factor as well. Again, we saw on a previous graph that men perhaps have higher rates than women, and that's for most types of cancer. And the question that remains here, and the question that I want to spend more time on today, is whether or not region and deprivation are also significant factors for mortality, for cancer incidence and mortality. So starting with regional variation, regional differences for cancer rates, what we have looked at in this work is the 9 different regions in England, as you can see them on the map. And I should apologize here in advance that we haven't In this work, the work that I'm going to talk about today, we will not consider Scotland. I'll come back to this later on in my talk. Well, obviously on the map here, there are other parts of the UK, of the United Kingdom missing. The sub-questions, if you like, that we wanted to investigate here is that, well, if we, as we will find, if there are regional differences, we want to look at particular patterns. Is there some geographical pattern in those cancer rates? Do these differences change over time? Does the variation change over time? And is it the same or different for different types of cancer? So on this graph, we're looking at all cancer incidence, so incidence for all types of cancer combined. And this is for women, rates for women between 1981 and 2016. So on the vertical axis, you can see the rate, the incidence rate, and this is by year. So on the horizontal axis, that's time from 1981 to 2016. You can see 9 different curves on the graph, and these are the 9 different regions in England with different color here, together with probability, credible interval bands. So the first thing we notice here is that there's an increasing trend for all regions, and I think we've already mentioned that for these cancer rates. But the most important, perhaps, things we can see in the graph is that first, the incidence is higher in northern areas, northern regions. So the curves in the order you can see them are going from northeast to northwest and so on. So higher incidence rates in the north. And then the gap, if we're looking at the gap between the incidence in the region with the lowest rate and the incidence in the region with the highest rate, this gap is actually increasing with time. And we can see that if we, for example, if we look at the left-hand side of the graph, the range of the rates in 1981 and compare that with the range of the rates in 2016, you can see that that range has actually become wider. Let's compare that with incidence for men at the same during the same period of time. Again, all cancer rates. The trend is mainly the same as before. We have increasing trends for all in all regions. The incidence is again higher in northern regions, northeast, northwest, and so on. Perhaps not so easy to see on this graph, but the rates are actually higher than in men compared to women. But perhaps and I think the most striking feature of this graph as compared to the graph that we had on the previous slide is that the gap now is not increasing. So the gap in between lowest and highest rates in 1981 is more or less the same as the gap in 2016 for men, whereas remember in the previous slide that gap was increasing for women. Let's now look at a couple of specific types of cancer. And now we're looking at, first, we're looking at lung cancer for women in a given year, in one single year in 2016. That's the last year in our data. And on the map, you can see the 9 regions in England. And the color here, the darker colors represent higher rates. So I think we can see that there's a clear distinction between different regions here in terms of the incidence rate. Perhaps there's a divide between a big difference between north and south. You can see the different colors there, the darker colors in the north. What we also looked at in this work is how the rate in each region compares to the, if you like, the national average rate. So the rates over all 9 regions. And what we found here is that the region with the highest incidence, that's the Northeast, that has a 35% excess rate compared to the average. Whereas if we look at the one with the region with the lowest incidence, the Southwest, that has a 28% lower incidence rate compared to the average. London there is about in the middle. It's about is very close to the national average for lung cancer incidence for women. So clearly a geographical variation for lung cancer for females. Let's now contrast that to breast cancer. Breast cancer is, as opposed to lung cancer that we were looking at before, is not a lifestyle cancer, what people call a lifestyle cancer. And that is now reflected in the geographical regional variation that we can see on the map. The rates are very high, perhaps higher than the rates for lung cancer that we were looking at before. Breast cancer is the most common cancer in women, but the variation now, the differences between different regions, the shades on the map, if you like, are not very different as before. And again, this is most probably because of this type of cancer not being related to lifestyle. So our next question was about socioeconomic differences in cancer rates. So in this work, as an indicator for socioeconomic status, we use the index of multiple deprivation in England. This is a widely used metric, which is based on information on income, employment, education, and so on, in small areas, as you can see on the map in England. And according to this index, the IMD, the population in different areas is divided into 10 deciles, with decile 1 being the representing the most deprived part of the population, and decile 10 representing the least deprived part of the population. So let's first look at differences with respect to deprivation for lung cancer incidence for women between 2001 and 2016 now. So what you can see on your screen now is 9 different plots. Each plot is for one of the 9 regions. And within each of those plots, you can see 10 curves, which now represent the 10 deprivation deciles. So perhaps the first thing we can notice here is that the rates are higher for the most deprived. So the top curve on each of these graphs in all 9 regions is the rate for the most deprived part of the population, whereas the bottom line, if you like, the bottom curve there is for the least deprived. The deprivation gap, so there's definitely a deprivation difference here. There are differences with respect to socioeconomic status, and these differences, this gap is actually getting wider with time as well. As before with the region, we can see again on these graphs that the gap on the left, on the right hand side of each graph is wider than the range and the gap on the right-hand side, representing the 2001 year. So the variation is getting wider, and the differences, the inequalities here with respect to deprivation are more obvious, more evident in the northern regions. So, for example, if we look at the top row there in the graph, these are the northern areas in England, and you can see there that the differences are more distinct between the differences between the deprivation groups. So let's now focus on the comparison between the rates for the most deprived with the rates for the least deprived. And again, we're looking at lung cancer here for females in 2016. And on the horizontal axis, you can see the rates for the most deprived part of the population, whereas on the vertical axis, you can see the rates for the least deprived parts of the population. So if the rates for the most deprived and the least deprived were about the same, we would expect to see most regions on this graph around this red line, the equality, what I call here the equality line. And as we move further to the right of the graph, then the differences between most and least deprived gets higher. So if we look at London, for example, this is the rate for the most deprived is about 2.5 times the rate for the least deprived. Whereas if we look at northeast and northwest on this graph, then the rates for the most deprived are about 3.5 times the rates for the least deprived. So there's a huge difference between most and between the rates for most and least deprived here, and there is also regional variation in the sense that deprivation difference, the deprivation gap, is different in different regions. Let's look at the same type of graph for all cancer incidence for men now in the same year. Now we can see that all regions actually lie close to the 1.2 times line. That means that the rates for the most deprived for all cancer incidence for males is about 1.2 times higher than the rates for the least deprived. So again, a big difference, but not as big as for lung cancer. And this is mainly because when we look at all cancer rates, incidence rates, the differences are the deprivation. The differences with respect to deprivation are lower because we have other types of cancer coming in, which are not necessarily what we call lifestyle cancers. And the difference here, the differences in different regions are about the same with respect to deprivation. All regions are about, the rate for the most deprived in all regions is about 1.2 times the rate for the least deprived. Now, as I said at the beginning, I'm going to say a little bit about mortality in this presentation. So mainly I want to show you some findings which are similar to the ones that we had before, but perhaps with one important difference. So let's look at this graph similar to what we had before. Now we're looking at mortality, all cancer rates, women between 2001 and 2016. Each region now shows, again, a different, each plot shows a different region, and within each plot we have the 10 deprivation deciles. So again, as we saw with cancer incidence, we can see that the mortality rates now are higher for the most deprived. The gap between 2001 and 2016 now is increasing, and I'm talking about the deprivation gap here. But the main difference from what we were seeing compared to what we were seeing before is that mortality now is, in most cases, dropping, which is good news in itself. But then if we look a little bit closer at this graph, we will see that mortality is dropping, but not for all different deprivation groups. So, for example, if we look at the middle row there, East Midlands, West Midlands, and so on, you can see that the top curve there, which represents the most deprived, mortality rates for those groups is not actually dropping. Whereas the mortality rates for the least deprived, the bottom curve, the pinkish curve, if you like, on these graphs, is actually, the rates there are actually dropping. And more generally, in all regions, what we see is a drop, a fall in mortality, but the mortality rates are dropping faster for the least deprived. Now, The last part of my presentation today is about the impact of delays in cancer diagnosis on cancer mortality, on cancer deaths. So I think this is very relevant and very important these days as well. I'm sure that most of us will have seen in the news. What I have here, well, is an extract from the BBC website, mentioning that cancer diagnosis fell about 40% since the start of the pandemic. So what we want to do here is to see, to quantify, using our modeling, the impact of such delays in cancer diagnosis on mortality. And the way we did that with our modeling was to start by estimating the average age at diagnosis using the cancer incidence data that we have. And we did that for different regions, different deprivation groups, and so on. Then we include that average age at diagnosis as a risk factor in our mortality model. And what we found there was that this was, as perhaps expected, a significant factor for mortality. And then we generated scenarios, assuming, for example, a 3-month or 6-month delay in diagnosis, and looking at what the impact of that would be on the number of deaths, on the mortality rates, more accurately. So in this work, we started by looking at a 3-month delay, and then we moved to a 6-month and a 12-month, a 1-year delay, as we found out that the pandemic was more persistent than we expected at the beginning. So let's look at what we found. So first, looking at a 6-month delay for lung cancer for women. You can see on your screen there the 9 regions, and at the bottom of the screen is a scale showing a percentage increase in mortality for that 6-month delay in lung cancer diagnosis. And what we can see here is that for all regions, a 6-month delay is causing at least 60% increase in mortality. And this is also allowing for and accounting for uncertainty. Those bars that you can see for each region are 95% credible intervals. So a very, very significant, very important increase in mortality as a result of a 6-month delay in diagnosis. Let's fast forward to a 1-year delay, 12-month delay in diagnosis for lung cancer. Now you can see that the increase in mortality is alarming. The variation is a little bit bigger, higher for different regions, but you would perhaps expect that as we are looking further ahead in the future, if you like. But what we have found is that a 1-year delay can potentially cause a 150% increase in mortality rates. And in all cases, what we found was that that impact was higher in London as compared to other regions, which is a finding that it was a little bit surprising and interesting compared to results, earlier findings where we found that London had perhaps more favorable findings, outcomes with respect to cancer rates as compared to other regions. Now, I think I only have 2 more slides, and what I want to do is to first summarize what we have found with this work. So if I had to summarize our findings so far in 2 bullet points, I would say that first we found that the gap, the regional and deprivation gap for cancer rates is widening with time, which is not good news. But the good news is that it's not widening for all types of cancer. There are certain types of cancer that this gap is remaining the same or even decreasing a little bit. The second important finding was that a delay in diagnosis for certain cancers can lead to an alarming increase in the number of deaths. And this, again, is true for certain types of cancer. But both these points, I think, lead to a question about whether or not public health interventions at both the regional and deprivation level should be more effective. And finally, let me just say a few words about where this work is going and other future directions. So first of all, we want to look more closely at the impact of the pandemic, the impact of COVID-19 on cancer incidence and mortality. And we're doing that by now using more recent data from the last couple of years to actually estimate the impact of the pandemic. We also, as I said at the beginning, want to include Scotland in this analysis, and we are now collecting data, well, not actually collecting, but getting access to data in Scotland, cancer data in Scotland. The reason why we had not included that from the beginning was that the data come from different sources. So we have now been in touch with Public Health Scotland, and we, as I said, we are getting access to Scottish data. We are also very, very interested in whether and how we can actually project cancer incidence into the future. And there's definitely ways to do that within our framework of models. But a challenging point here is, for example, how do we account for new diagnostic procedures, new screening programs that will obviously affect the cancer registrations, the cancer incidence. And finally, on a more general note, if you like, what we want to do is to use our expertise in statistical data science to bring together topics that I'm particularly interested in. For example, the evolution of infectious diseases and how this is linked with health and insurance. So I will stop here. Thank you very much.